And so when we look at many applications, we see that they are re-executed again and again on slightly changing inputs. The examples abound. For instance, spell checkers look for spelling mistakes as we make modifications to a text file, or search engines periodically crawl the ever-changing web. Another example is software build processes, which respond to source code changes as we develop our programs. And in all these cases, we want the programs to be efficient for not only the incremental run, but for all the subsequent runs that we make a change. So the idea of incremental computation is to benefit from this possibly repeating computations. So in the first run of the program, in the incremental computation, we store these intermediate results. And then in the incremental run, we try to reuse as much as possible to speed things up. So let's look at a concrete example of a build process for a software project where we have a bunch of source files that are compiled down to object files, and then these are linked to get an executable. So if you make a single change to one of these inputs, rather than re-executing everything from scratch, the idea is to only update things that depend on the change. And for the parts that stay the same, we try to reuse the results. So in this example, even though it might look like complexity-wise we don't gain much, but imagine that we have tons of input files of which only a small part of the inputs change. Then there's a potential benefit of reusing much parts of the computation and gaining more speed up. And at the heart of incremental computation, there's a technique called change propagation. So for change propagation to happen, in the initial run of the program, we build a trace of the computation. By trace, I mean a dependency graph of the inputs, intermediate values, and the outputs. Then in the incremental run, we propagate these changes from modified inputs towards the output, and only updating parts of the computation that depend on the change. And for parts that stay the same, we reuse. So in general, this change propagation could bring us lots of speed up when the dependency graph is wide and shallow, or programs have data level parallelism. So now that we have this new paradigm of programming, this incremental computation, and that we have the existing language-based techniques like self-adjusting computation that can handle this incrementalization automatically, like you write a program and under the hood all this incrementalization taken care of, what we want is actually a high-level framework to verify upper bounds on the incremental update times of programs. And here I mean verify, because our goal is not to infer. Even as you'll see in the rest of the talk, these bounds are a bit complicated. So we want to verify these bounds, not to infer. And doing this analysis of verifying upper bounds on algorithmic analysis or on pen and paper work is very difficult most often, because it requires you to reason about two executions of the program, the initial run and the incremental run and their interaction. And most often this depends on the dependency graph, this trace, the input changes, and the underlying change propagation algorithm. And even an input change can force the dependency graph to change the structure at runtime. So that's where R comes in. We are interested in developing a type theory to structure proofs of the update times of programs. As the first step towards this goal, in our previous work, we have developed COSTID, which is a refinement type and effect system for establishing incremental complexity of a program. COSTID combines size and changeability refinements and obtains the update time of a program as an effect. And its analysis is purely relational. By that I mean that the program, two runs of the program, initial and an incremental run, assume to be following the same execution path. So COSTID's analysis is attractive because with having this high-level type system, we can easily reason about the update time of a program, and it's also compositional. But COSTID has two major limitations. The first one is a bit technical, but it is that soundness of COSTID is proven with respect to an abstract change propagation semantics. By abstract, I mean that we have a bunch of structural rules that tells us how change propagation occurs. But apart from example, benchmark programs, that we don't have enough evidence that these abstract change propagation semantics can be realized in practice. Secondly, and most importantly, costed prohibits structural changes. By structural changes, I mean that changes that require the execution path of a program to diverge. For instance, in costed, input changes that influence the control flow of a program are forbidden with stringent typing restrictions. So in this work, we present do-costed, which is a redesign of costed to address these two limitations. Do-costed comes with a realizable change propagation semantics, and it allows structural changes. But its core, it's still a refinement type and effect system. So in the rest of the talk, I'm going to mostly focus on the second part, that is how we allow structural changes. And then towards the end, I will come back to the first point. So let's look at how we allow structural changes. So in costed, we establish an upper bound on the program by typing it with a typing judgment where this cost kappa establishes this upper bound. But it assumes that structure of the trace doesn't change. That is, we always take the same execution path. But this means we cannot analyze a program like a conditional, where in the first run we take the then branch, so x is true, and we build a trace. And then incremental run, if x is updated from true to false, we are in trouble, because there is no trace to change propagate from. So costed cannot reason about this. But in do-costed, we can reason about this by taking into account that in the incremental run of the program, we might have to execute things from scratch. So we have to establish an upper bound on their from scratch execution time. Therefore, do-costed comes with two typing judgments. The name do coming from like double, double. So for the case where we might have to re-execute things from scratch in the initial run, like we take the else branch, we have a from scratch execution judgment where we estimate the worst case execution time of the program. So kappa is a unary effect. That is, it only reasons about single execution of the program. And for the cases where we might have to keep change propagating, like staying in the then branch, we have another judgment for change propagation, where the cost kappa is an upper bound on the change propagation time, and it's a relational effect. That is, it reasons about the initial run and the incremental run. But surprisingly, the interaction of these two judgments leads to non-trivial changes from the type system of costed to do-costed. And the rest of the talk, I'm going to talk about how these interactions happen. And then I'm going to show you an actual example, merge sort. So let's start with an overview of do-costed. So on top of a standard typing judgment, in do-costed, we have an effect, kappa, which specifies an upper bound on the cost of either change propagation or from scratch execution, depending on this typing mode epsilon. And since we have a refinement type and effect system, these types, input types and the output types, talk about refinement types. So let me show you high-level ideas behind the type system and mostly talk about how these refinement types interact with the effect. So let's start with a very simple example. Program x plus 1 with one input x of type integer. Assuming that plus operation takes unit cost, we can type this function with one from scratch execution cost, right? But what about its change propagation cost? Well, in the worst case, we might have to re-execute everything from scratch. Hence, we can give it, again, one cost. But what if we know that x is not going to change? Can we do better? Well, of course. In this case, we don't have to re-execute everything from scratch, right? We can reuse for free. Then we can give this program zero cost. But how does the type system specify that something is not going to change? There we borrow ideas from informational flow control. Like we annotate types with high and low information. In do-costed, we annotate types with changeable or stable annotations. So if something is not going to change, we annotate it with S, standing for stable. And then this can be propagated to the output type. And if something might change dually, then we annotate it with C, standing for changeable. And then this can be propagated to the update type, and we get one from scratch execution cost. Another refinement in do-costed is for input types. In particular, list types are refined with the size of the list, because most often the cost of a program depends on its input sizes. Moreover, we also annotate a list with alpha for incremental runs. So alpha specify maximum number of elements out of a list with size n that are allowed to change from initial run to the incremental run. And of course, we can quantify over this n and alpha. And for function types, we can quantify universal and existentially, and then we have another refinement for function types. So function types track the cost of the body, and this cost depends on which mode the function is typed in. So if we look at the lambda x dot x plus 1, this previous example, we can give this function 1 from scratch execution cost, because we are doing unary reasoning about single execution. We don't care about its input and output annotations. If we want to do a relational reasoning, we can give this function 0 change propagation cost if it takes stable inputs to stable outputs. Or dually, we can give this function one change propagation cost if it takes changeable inputs to changeable outputs, because here we might have to re-execute. And now let's see how these typing modes, typing annotations S and C, interact with the typing mode epsilon. So let's look at the conditionals. So if we know that the guard of a conditional E can be typed with a changeable Boolean, that means its value might change from true to false or vice versa. In the incremental run of the program, we might have to re-execute parts of the branch from scratch. Therefore, we type the branches in from scratch execution mode. Moreover, we have to make sure that the result type is also changeable, because the then and else branches can be unrelated. Otherwise, we keep change propagating. That is, if the guard is a stable Boolean, that means we take the same path in the both runs of the program, we keep change propagating. So type the branches in the change propagation mode. So the general idea is that whenever we are eliminating changeable functions, these are functions that themselves might change, or some types of which conditions are a simplification, the continuations must switch to the from scratch execution mode. So the point is that whenever we branch on something changeable, we have to give up this relational reasoning and switch to this unary mode. But if something stays in the relation, that is, its value is, well, it's in the related by the Boolean type, we can still stay in this relational reasoning of change propagation. And now let's look at an example, in particular merge sort. So assume that we want to sort a list using the merge sort function. It takes a list and splits the list into two lists, L1 and L2, and recursively sort this list and then merges them using the merge function that takes two sorted lists. And if one of the lists are empty, it returns the other. Otherwise, it looks at the heads and then takes the smaller one and recurses on the rest. So what can we say about the incremental behavior of merge sort? So let's look at its abstractly its trace. It's bottom-up view of the recursion tree where we have 8 elements. So let's start easy. Like, what happens if we change all the elements of the list? We change everything. What can we say about its incremental complexity? Well, since we have to re-execute everything from scratch, right? Its incremental complexity will be equivalent to its from scratch execution cost, which is n log n. But what if we make alpha elements? So we change alpha elements out of this list. Say we make 2 changes. Well, in this case, we don't have to re-execute everything from scratch, right? It will be better than n log n, because we'll be reusing the parts that didn't change, only updating things that depended on the change. So in this case, by doing a clever counting argument that counts the amount of work done at each level, we can show that it has this bound. Since we are counting all levels, we'll get sum over the log n, but the point is that I don't want you to read this whole thing. I won't explain it. The details are in the paper. But this bound is in this nice complexity, n times 1 plus log alpha. So if alpha is equal to 1, we'll get linear incremental update time, which is much better than n log n. And if alpha is n, we'll get n log n, right? And let's see how we can verify that actually merge sort has this cost. So we are assuming we are given this cost, and we want to show that merge sort has this bound. So let's look at its definition again. And what I want you to observe here is that even though the recursion structure of merge sort stays the same, the recursion structure of merge is highly dependent on its values, the values of its elements. So if the value of x less than y changes from true to false, we might have to take a branch that was not executed before. Even number of calls to merge might change because of this, okay? Hence, we need to switch to this from scratch execution mode, which was not possible in costed. But in do-costed, we can type merge with this from scratch execution mode. Since it's called recursively in these branches, we can give this function merge, this type, with n plus m complexity, okay? So it's from scratch execution will be linear in n plus m. And let's see how we can combine this to type merge sort. And I will be focusing mostly on recursive part. So our aim is to show that merge sort given a list with n elements and alpha changes can be given this bound p and alpha. Okay, I won't explain like the details, but I want to show you how we can intuitively get this bound. So our aim is to show that the body of merge sort can be given this p and alpha cost. And I will focus on the recursive part. And we want to show that this p and alpha is enough to pay for the cost of the body. So let's look at the body. So in the body, we have B-split. So it can be shown that B-split, because it does is rearranges its elements, so it doesn't do actual computation, it can be given zero change propagation cost. And if it has alpha, if it was given alpha elements, it can redistribute these elements so that if the first list has beta changes, the other one will have alpha minus beta changes. So we need to show that p and alpha is enough to pay for the cost of B-split, 0, plus the cost of the recursive functions, L1. Inductively, we get Pn by 2 and beta, plus the other recursive cost, Pn by 2 alpha minus beta, plus the cost of merge. So merge can be given this type with from scratch execution cost, and we can combine this to get the cost, okay, n by 2. So here I put a linear function, but it's a linear function, so h is a linear function. So what we have done, in a sense, is that we have reduced the type checking problem of merge sort to this arithmetic constraint, okay, which can be discharged. For the case where alpha is equal to 0, we'll need to do some additional work, but this is like in costed. And then we can type this function with p and alpha cost from end to end, including the type of merge. So far we have looked at how the type system work, how do costed's relational, this two-moded analysis allows us to make structural changes. And next, I want to talk about soundness. So in do-costed, you prove soundness with respect to an abstract change propagation semantics, like in costed, because it's easy to reason about and tells us what needs to be done, but it doesn't come with an actual algorithm. So we also prove the soundness with respect to a concrete change propagation semantics, where we have actually a change propagation algorithm. So this is, the algorithm itself can be obtained by doing a type-directed translation. So in the process of translating a derivation, we get a program in the target language with references. And so in this translation, we record the dependencies explicitly in the trace. And then in the incremental run, we propagate these changes from the bottom up and only getting the things that depend on the change. I'm overly simplifying here, but the details are in the paper. But the point is that what we actually want to show is that the cost of change propagating this target program with its trace is upper bounded by the cost kappa estimated by the type system. Of course, we also have another case for where we have from scratch execution of the target program. And we do the proof by building two-step index logical relations. One for change propagation, which is relational, and one for from scratch execution, which is unary reasoning. So overall, I have shown you that reasoning about incremental complexity can be challenging because we have to think about all these underlying details. But once we have the right level of abstraction, for us, do-costed, which provides a refinement type and effect system, which combines this unary and relational cost analysis. Unary in the sense that we have a thing from scratch execution, and relational in the sense that we have this change propagation reasoning. And the interaction of these are mediated by refinement types. So combining these, we have obtained an expressive and sound type system with realizable change propagation semantics. And in our follow-up work, we have implemented a bidirectional type checker with a backend to an SMT solver to solve these constraints like I have shown you. And also, even though the focus has been here in incremental computation, the design of the type system can be generalized to other kinds of relational costs. For instance, to show that one program uses less resources than the other, or to show that two programs use the same amount of resources for the purposes of timing side channel attacks, or for the purposes of compiler optimizations, which is submitted to Popple. Okay. And with that, I would like to thank you. And I want to also mention briefly that I will be soon on the job market for the next year. So, okay. Yeah. If you are interested in this kind of work, I'm also interested in, or any kind of industrial research positions or industrial positions related to functional programming. And with that, I would like to conclude. Thank you.
Thank you very much. We have time for a couple of questions before we finish up. So, as usual, state your name and affiliation. So.
All right. Hello, Dakota Fisher, CU Boulder. One of the questions I have is about some related work. So I've been working on this thing called Adapton, in which change propagation, it actually, in a sense, happens twice. There's one step which propagates the fact that there is a change, but it isn't recomputed until later.
Lazy style. Well,
Yeah.
demand-driven. Okay.
Do you think that that Ducostic could be further extended to encompass this as well?
Yeah, I think so. That's possible, but you need to take into account that the change propagation algorithm is a bit different. And with the laziness, there would need to be, changing some parts of the design, especially the algorithmic change propagation part, I think. But the design of the type system is general enough to handle relational codes. So I believe that's possible, right?
Okay.
Takayuki from Bricken. Excuse me. So this type system seems to be very powerful, like kind of understanding the integer arithmetic as well as maybe logarithm. So how do you implement this type system?
Yeah, we have a bidirectional type checker,
yes.
so that you have minimal annotations only at the read axis. And then once we do type checking, we generate a bunch of constraints. And these constraints needs to be satisfied so that the program can be typable. But the constraints are challenging, like I've seen logarithms. So with intervention of several lemmas, we use the wide tree tool. With some several lemmas that can be dealt with logarithms, we can actually type check many programs.
What kind of tool do you use to solve those lemmas?
So currently we have mathematically solved one lemma, which is very generic, like a recurrence relation, fn plus like n by 2 with two functions. And then this can be mathematically solved. We just stated this lemma, but this lemma can be instantiated at whatever n or alpha you have given. And we have a linear function or constant function depending on which kind of a function, which kind of a program you're analyzing. So we have used alt ergo to eliminate these constraints, but for existential elimination, we have our own backtracking algorithm to eliminate the existentials because we have, disjunctions, conjunctions, and yeah.
Okay. So let's all. Oh, we have one more.
Yeah. You mentioned that.
State your name, please.
Oh yeah, sorry. Gabriel Scher, Northeastern. You mentioned that some of the older work on this learning static and changeable parts took inspiration from the information flow ideas. So you seem to have a general enough system with this binary. Can you go back there? Is there a way to think of your system in terms of information flow?
Right. Yeah, you can think of it like this, and you can think of this as pure refinement of this information flow control, the work by Potier and Simone, and where our S and C annotations correspond to low and high annotations. So if something Yeah, and in terms of the proof technique, the proof of this work is done syntactically, whereas our proof is semantically. So I guess our proof technique is also interesting in this regard. Yeah, and we can go back to information flow control, or like I've said, other kinds of relational analysis. Yeah.
Okay, so let's all thank Ezgi one more time, and that's the end of
Thank
the
you.
Sorry, there's one last announcement before.